I'll be chatting on Southwest Light Rail. I'm feeling pretty much everyone on the call here is at least somewhat familiar with the project. It's a pretty massive one, biggest construction project we've had in the state of Minnesota, and been a pretty politicized project. So it's been, well covered in the news and things. So try to keep it somewhat, not dive into too much that you've already heard about, hopefully. And I'm going to focus on one of the bridges where we seem to run into a bunch of different issues, some related to design, some related to construction, and kind of what some takeaways were from those. So I can skip over to who am I introduction. Craig already got that. What I'm going to kind of run over here, the presentations of just a very brief project background, some design discussion on how the size of this project really kind of drove some decision-making processes and things like that. Jump into the construction discussion that'll be primarily focused on the 9 Mile Creek Bridge, and then some kind of takeaways of things that we've learned along the way, and different ways we've had to handle some of the odd things that we've had to deal with the project. So the project itself, it's 14.5 miles of track going from downtown Minneapolis to Eden Prairie. There's more than 10 bridges in that in the project, over 15 retaining walls, 5 stations, 2 tunnels, and then also a bunch of private utility relocates. There's freight rail relocation, public utilities construction and relocation, maintenance of traffic. Maintenance of traffic, a lot of the segment is on existing pedestrian trail pedestrian trails. So there's a lot of detours that have been established, and a fair amount of traffic disturbance realistically, and then also some stormwater stuff. So kind of really just saying, yeah, here it's a big project and there's a lot of different components to it is really the main point of that slide. Going into the presentation here, design versus construction, try to look at what did we do right and where did we come up short, or what decisions or did we miss something on the design side? Did construction drive decision-making processes during construction? And what can we learn from moving forward on this type of project? So some kind of the big picture stuff that was influencing design. So generally a pretty risk-averse design team. It makes sense. It's a massive project. It's 75-year design life. Public transportation. It's understood that there's some risk adversity there, but at the same time, we got a little bit handcuffed to going into design on some of it, where we weren't able to be innovative or use techniques that aren't familiar with the rest of the project team. And then also the owner's construction team, which is different than their design team, was definitely conservative. One of the favorite phrases is "when in doubt, drive it stout." Basically, they're used to using driving formulas that say if you don't drive it to near refusal, the pile doesn't have the required capacity and you may have performance issues. Budget and political constraints. The project went through multiple rounds of bidding, having bids rejected, and some funding issues. Some of that political constraint comes into relying on a combination of state, local, and federal funding, and raising that funding is difficult. And the project had several areas with pretty substantial local pushback from the population. And again, the options brought forward but not being used, that kind of touches on what I already mentioned. We had things that we had suggested, attempting of, looking at doing load transfer platforms instead of a bridge, or doing a rigid inclusion instead of piling, or whatever it might be. And it was basically that we were handcuffed to do what they're comfortable with. And then once it got to construction, the contractor is now asking, hey, can we look at changing design here? And we think we can do this more economically. While they're continuing on just the general big picture design considerations, the heavy civil construction regionally is generally pile supported. When it comes to bridge construction, it takes something odd to have it go to spread footings or drilled shafts or something that's not a driven pile. And some of that is like I said, it's what we're familiar with. It's what it works. It's tried and proven. And we have a large competitive market with the contractors here on driven pile. The train braking loads were really high, so we were dealing with trying to account for pretty high lateral loading in the design. There's substantial vertical loading. We have some bridges with really large spans that result in some high pile capacities and large foundation elements. Pretty much the entire stretch of our alignment has bad soils, quote unquote. Wetlands, swamps, landfill. We have a bridge that goes through a stormwater pond that's above a MSE block wall. There's a lot of things that are unfavorable to grade supported track construction. As I've touched on, there was some political pushback, which led to difficult property owners and us not being able to get access to areas that we weren't allowed to cross through properties with any personnel at all, let alone with the drill rig. And all of this really led us to the project having just a lot of driven pile being installed. And some of that site access, who knows if maybe we could have had less piling on the job, but if we didn't have borings close enough to make a sound decision, it was basically pushed to driven pile. So the 9 Mile Creek Bridge is what we'll be chatting about kind of on the construction side. The green line that you can kind of see here, I didn't realize this is kind of a lot of area, is the track alignment. 494 down here and 169 for those familiar with the local region. And this bridge itself is this little curve through here all the way to over Flying Cloud Drive. So that stretch right there is the area we're looking at. This is our boring location plan overlaid on an aerial photo. You can see we're in a swamp that's wetlands, shallow groundwater. The yellow borings are the borings we completed, and the orange borings are the borings that were planned but were never constructed due to site access. And you can imagine here that puts some uncertainty into our design when we've got borings for roughly half the length of the bridge and half that we were unable to access. And that access comes in with this being this is just the street view from Google on the site. Right now we're looking at kind of the straight section where the street view car is parked somewhere here looking that direction towards the upper left of the screen. And you can see that looks like some difficult access, but maybe not impossible. Some high weeds and things. The next picture here is just showing how quickly that swamp drops off. The alignment is behind those first trees, and so we really just didn't have access. And this is looking north on Flying Cloud now, where the bridge crosses over the road and goes up the hill and into decent soils on the east side of this road. Just an example of a typical boring log from this area. You can see we've got 40 feet of peat and fill overlying some decent glacial soils. Outwash sands with pretty good blow counts in the 30s, 140, and then a mix of glacial till below that with mixed bags of sand and clay. And that sandy lean clay at the bottom extends to the end of our boring at about 130 feet. So we never really get into the traditional hard bearing layer that we see on a lot of our projects. Bedrock was deeper than what was reasonable to be driving to. We didn't even encounter it in our boring. So we're in a position where using the traditional driving formula that is accustomed to is less favorable, and we pushed hard to use high strain dynamic testing or PDA testing for this entire bridge. Jumping back to the design side of things. So this project got stretched. The design phase of it, we started in 2013 and started construction in late 2018. Initially, we used the Driven software program, Driven, which is a program established by the FHWA, a very simple basic pile design program that is no longer currently supported on Windows, which shows you how long the design phase got stretched out on this. We switched to using Unipile, which is a more robust software and allows for better functionality with MnDOT's drag load policy. So anytime we're dealing with any fill, so primarily at the embankments, drag loads have to be considered for the Driven pile. And that switch from using Driven to using Unipile, MnDOT issued a new drag load policy that was a substantial change, and so that was something we had to learn how to do in Unipile. And then we also had to figure out, what do we use for parameters to pass a gut check for what we're used to seeing for resistances, and what our testing that we've done regionally has shown for unit resistances. And then the Unipile is able to do a bunch of different methods for pile analysis. We use only two for the duration of the project. The beta method effective stress for SPT, and then the Islami and Fellenius for CPT. These are just examples of unit resistance graphs that we generated for the structural to evaluate the pile's capacity versus depth, or resistance versus depth. The first one is from an SPT boring. The second one is from a CPT. So you can see the CPT provides more data points, and the changes between soil layers become more gradual and more representative of what's truly there in the field. And we've had good luck with the CPT data using the Islami and Fellenius method, correlating well to capacity shown with testing in the field. We had to also provide the uplift resistance, which we reduced the skin friction calculated by 80%. And then after running through several iterations and taking, kind of the shortest pile and the longest pile on the project, doing sensitivity analysis, we were able to come up that nothing's going to have less than a nominal uplift resistance of 25 tons. And unless you need more than that, we weren't going to provide any further, we weren't going to do any further uplift analysis. The drag load, as I already touched on, we were using the new method that was initially based on a design memo. It wasn't incorporated into the plans yet or the design manual. But by the end of the design phase, it was. And so it was part of these specifications. The new method results in higher drag loads than the old method, but isn't a reduction in the resistance. So you're able to look at your full profile. The old method kind of said, if you've got drag loads down to 20 feet, you wouldn't rely on any skin friction through that layer, and that's no longer included. So, kind of an example of an improvement in the design policy that occurred during the project. And then for the last piece of the design that we performed was the analysis, the lateral analysis. So during our reports, we ran analysis in Alpile. We based it on deflection requirements and not on actual loading. And that was used really only to give the structural engineers a reasonable starting point for what might be an acceptable lateral shear load at the top of the pile. The final analysis was done by the structural engineer using the FB multi-peer software that allows the whole bridge to be modeled as a system and is a more accurate determination of deflections and stresses, especially when we're dealing with soils that are not uniform, and you may have different stiffness parameters from one substructure to the next. So ran through our design and provided pile lengths to MnDOT that were based on their maximum factor design load. So we said that we're going to assume the most efficient design possible, that on a 12-inch pile, you can put 100 tons. On a 16-inch pile, you can put 140 tons, with, based on provided docs from MnDOT. It's a fairly common approach to bridge design. And we looked at multiple pile sections for each bridge. We also took a somewhat conservative approach to the pile length of, just because the embedment graph said we had capacity at a certain elevation, if there was a very dense layer deeper than that, we would go ahead and say you need to plan on the pile extending to that deep layer. That, hanging it up may or may not happen. And then we also rounded all of our pile lengths to the nearest 5-foot increment. So we then went into a design iteration process here. The project funding came into question during design. We actually had to shelve the project, stop working on it completely for a short period of time. The costs, route, all of that came into question, and they've started really saying we need to save every penny we can. How can we get there from every aspect of the project, but including what can we do as geotechs to help reduce costs. The project as a whole has roughly 650,000 linear feet of piling, which is obviously a lot of steel piling. It's bid at a per foot of pile installed for how the contractor gets paid on it. So changes in length during construction are potentially a direct change order or direct savings to the owner. I don't know how often we come in short, but we started having discussions in design meetings on, if we save 1 foot of pile on each pile across the project, that's a $27 million savings to the project. So they got very focused on fine tuning our pile lengths. So want everything down to exactly where we need it for capacity. We went through multiple iterations of revising design loads, and the structural provides us with a revised load, then we provide a revised length, rerun analysis, and it produces a slightly different result, and we're back at the beginning again. And so we went through that, and as I showed on that boring for 9 Mile, we don't have a hard bearing layer. And so restriking of the test piles and select production piles was determined to be the best way to reduce pile length during construction, and to be relying on 100% of your skin friction, which means you have to wait for your pore pressures to dissipate to see that capacity. They also brought into question the field quality control method of, instead of doing PDA on everything, let's use MPF 12 if it makes sense to do so, which is MnDOT's pile driving formula from 2012, which is where the creative naming came in. So that was, initially we were going to do an entire bridge with the same field quality control method. Didn't really have many where the whole bridge made sense to do that. So we switched field quality control method across the board to be a substructure by substructure consideration. So through all of that, we end up with this messy, convoluted spreadsheet that you probably can't really make much sense of, but it shows some of those iterations, and then some of the things like what the design load is, what is our minimum depth to achieve fixity, or minimum depth for lateral loads. We've got actually 2 different columns on there for that. One is from L-Pile and one's from the FB multi-pier. Generally, the FB multi-pier resulted in the need for a deeper pile for fixity. And so that brings us into construction. This is just your quick plan sheet, again, showing the alignment coming down through the swamp and then over Flying Cloud Drive. Starting with trestle bent piers that are very closely spaced, moving to traditional hammerhead piers that are further spaced as you move to the north and the east. We started doing production piling, and everyone is questioning how are we doing on design lengths. And so just a very quick example of a few of the substructures here. The left column is our original estimated pile length. The center is the final estimated pile length after the rounds and rounds of iterations of revising lengths and revising design axial capacity. And then the furthest right column, or second to right column, is what we actually installed for the average production pile for that substructure. And what you could take away from this is the structures where the EOID criteria means that we did not do a restrike, the pile was driven to full capacity on the initial drive and they kept driving. The 3-day restrike is just that. We let the pile sit for 3 days, did a restrike, and we're able to come up with kind of a fine tuning of our driving criteria. And the locations where we did the restrikes, our final estimated length was close. Where we didn't do it, there was substantially longer pile for at least 2 of the 3 structures, or 3 of the 4 structures that didn't have a long-term restrike performed. So some of the other construction difficulties that resulted in why we didn't do restrikes are the pile bents are a small, quote unquote, small structure. They only have 7 pile in them. The contractor wants to pound those out in a day, and having to wait 3 days to do a restrike means that they're not moving the crane to the next location. They're looking at delay claims. The construction schedule starts being considered, and the decision made by the council is let's drive the pile deeper, do it on initial drive, and not have that 3-day delay. And so this is one of those examples where the construction and the design kind of saw things a little bit differently. The design says, hey, we planned all along that we need to do these restrikes, and construction says, we got to go. Look at schedule. We're already buttoned up against critical path items here. And ultimately construction ended up winning. Some of the other issues with this site were site preparation, location tolerances, plumbness tolerances, and then we had some damaged piles. So you can see the slope that they're working on in this picture is definitely not a nice flat working surface. It's working down into a swamp, and they're provided working points. And then their field guys are pulling tape measures off the working points to lay out the piling, which is very difficult to achieve when you're working on a slope and you're not GPSing each location and shooting those in. So we ended up having some location tolerance issues. And then similarly, some piles that were out of plumbness because either encountering something at depth, or there are likely some issues associated with trying to work on a sloping grade like this. And this is just an example of some of the plumbness. You can see those piles are all supposed to be perfectly vertical, and you can see that they're not. Moving into some of the hammerhead piers, this is where we started seeing damaged piles. So during our inspection, the 2 piles with the 2x4 laying over it were found to be damaged. Had clearly had water in them and were flagged immediately. The pile second from the left corner here, this one, our field inspector sent me this picture saying we have these 2 damaged piles. And I immediately said, well, what about this pile here? Is that actually damaged too? Because you've got water flowing through the concrete, and it's a substantial volume of water, it appears. And they went back and back checked their notes, and that pile had taped out substantially shorter than what it was installed to, and was ended up being determined to be a damaged pile as well, even though it was already filled. So it was good that they took this picture, and we were able to capture that additional damage prior to the contractor having moved forward with anything besides filling it with concrete. So we had 3 out of tolerance piles, 4 damaged piles. Where do we go from here? You know, Gilbert basically saying, you know, the only thing we control now is who we blame, and yeah, that's right, but it's not we, it's you. So we went through several different repair options with the structural. They're working in, as you can see from here, that they're working in a cofferdam. It's all four sides are cofferdams, so they're very tight site constraints, which limits our ability to come up with repair options. We discussed micropile, different types of foundation, or different types of deep foundation options that may be able to minimize any change in the foundation footprint. Worked through it with the design team and ended up choosing to offset piles, redrive new pile. They still drove a 16-inch diameter pile, but they upped the wall thickness to help reduce the risk of damaging the replacement pile during the install. And we were able to do that successfully, even though what looks like a reasonable solution on paper when you get out on site ends up being a very tight configuration. The pile buck standing there next to that pile couldn't squeeze between the production pile and the replacement pile if you had tried to. So it was very tight, but we managed to successfully install them, meet capacity requirements. We monitored it with PDA during the installation to check for damage and to monitor for stresses, watch for damage indicators, and to verify capacity. And then the final pier I'll touch on is as we moved into that area of unknown or no boring logs of the orange locations, we started having issues meeting the minimum embedment depths required for the lateral. And we anticipate that was associated with densification of the granular sand layers. So this is one of the first piles that was installed, and this 25 to 40-foot zone is that sand layer that we noted in our boring log. And you can see we've got blows per foot of less than 10 on average across that whole zone. They continued driving pile in that area, and a week later, we're driving the pile and we're seeing blows in the 30s to 40s with pretty high hammer strokes, which means we're getting a lot of energy into the pile, and the concern for continuing to damage more piles moving forward is raised. And so we were able to get out, do additional PDA testing, and back off on our criteria to keep the shorter piles that are hitting this hard driving from having to be driven through that layer and extended deeper, with some of them having a difficult time meeting the minimum embedment depth, which was 25 feet. So, and then that's just back to that same boring again. So you can see that sand layer that shows up as fairly dense in the boring. Didn't seem that dense on the test pile or the first couple of piles, but picked up strength as we continued driving the pile. So some of the takeaways. So the estimated pile lengths were generally pretty close to design length when we were allowed to do the restrikes. But when we're looking at this in construction, we need to consider more than just the material, or sorry, we're looking at it in the design side prior to construction. There's more to consider than just the material costs. And that maybe looking at those locations where it's a 7-pile bent in a tight site constraint, maybe we don't plan for restrikes and they come into that budgeting the additional piling instead of having it become a change order. And then finally, the non-conformance items can be remedied. So we had issues. We were able to fix all of them. Required driving some additional piling, but didn't result in any substantial delays to the schedule. And the contractor was able to keep moving with relatively minimal additional costs. And then this is more big picture design takeaways for the job. Dealing with a project this large, we had design. We didn't have the same design team from the beginning to the end of the project. People change positions, people leave companies, get promoted, whatever it might be. And some of the decisions that were made for a reason on the front end, when they come into question in the back end and it's a different person, they may not have an explanation for why a design was done the way that it was done. And that led to some difficulties in trying to determine if value engineering was an option, or if we could use a different type of foundation or whatever it might be. And then we had some issues with, design and oversight, not always seeing eye to eye. Like I said, the restrikes versus not, and trying to mitigate that on the front end through, thorough communication is important on these projects. We're, huge scale on costs, and keeping our client, the owner, and the contractor all on the same page, and trying to keep costs at where cost and schedule as reasonable as possible is important. We've been handcuffed on the project a little bit by following project specifications to the T, where some jobs we might be able to work more directly with the contractor, or work with different foundation options. Here the project's just so massive, there's so many different moving pieces that if we do that in one spot, then it's going to be expected at the next, and that can lead us to getting ourselves in trouble. Whether that's a design change or a means and methods change or whatever it might be, when we're dealing with the scale that we are, following the documented specifications and contract documents is critical. And then the final one is communication. We've had all sorts of fun on communication between our own team, where we've got 45 full-time employees dedicated to a project, and then a handful more that are part-time. And then as well as between us and the contractor, us and the owner. Again, it's just a lot of moving pieces. There's a number, when we're working on 10 bridges with 5 of them being constructed simultaneously and multiple pile driving rigs on each bridge, scheduling our PDA testing can be challenging. And so there was some initial rocky roads on communication that have generally smoothed out to be working well with processes that have been established and agreed upon by all parties in the project. So with that, I appreciate your time. I ran a little bit long, but tried to keep it, I flew through some of that there. So if you've got any questions, please chime in. And then also thanks to our project partners. Beck Council is our client, Lunda and McCrossin, who are the contractor, and then American Engineering, who we're actually partnered with on the job.
Great.